Hello, everyone, and welcome to Talk Nerdy. It is Monday, August 15th, and I'm your host, Cara Santa Maria. Now, remember, everyone, Talk Nerdy is and will always remain 100% free to download. And the reason I can continue to keep Talk Nerdy available to everyone who's interested is because of listener support from folks just like you. If you want to support the show, you can visit my website at www.carasantamaria.com. You can shop in the Talk Nerdy store, where we have just replenished brand new custom handmade mugs and leather bookmarks. And you can also pledge your support for the show through various portals like PayPal and Patreon. Now, I want to give a special thanks this week to Matthias Fritz, who visited the PayPal portal and pledged a really generous donation. And Matthias hails from Austria. Thank you so much for that. And those of you who have visited my Patreon page at www.patreon.com/talknerdy, I thank you so much. And I want to give a special shout out this week to Phil T-Bear, Stuart Ogg, Rod Adams, The Honorable Husband, Charles Payet, Jafe, Gabriel Felipe Jaramillo Gonzalez, Brian Holden, and last but not least, Jeffrey Sewell. Thank you guys so very much. All right, I'm really excited about this week's show because I had a chance to sit down in person with Dr. Michael Habib. Now, he is a professor at the Keck School of Medicine at USC. He teaches gross anatomy, and he's also a researcher at the Dinosaur Institute at the Los Angeles County Museum of Natural History, where he does paleontology. And really, he focuses a lot on the biomechanics of extinct animals. He's interested in their motion and reconstructing what we know about how they function. It's fascinating stuff. I'm really excited to bring it to you. So without any further ado, let's talk nerdy with Michael Habib. So, Mike, thank you so much for coming all this way to my home studio in the blistering, I don't know why I said that, in the heat of LA.
No worries. I like a little extra sunshine. I produced some vitamin D on the way over.
Good.
Pretty fun.
It's funny, we've been sitting here chatting off air while I'm like checking levels and stuff, and there's so much good stuff. I hope that we can remake it all to the podcast.
I'll try to be even more amusing the second time.
Yeah, exactly. Please say exactly what you said last time, but funnier. You can do that, right?
That's kind of like what my students ask me on a regular basis in lecture, actually. Can you repeat that slower but funnier? That would be great.
So for people who are just tuning in, everybody's just tuning in. We are the only two that aren't just tuning in. You are a very interesting scientist, I think, in my view, because you do a lot of different things that feel disparate or seem disparate to the outside world, but really, I think, have a lot to do with one another in your regular dealings. So the main thing that I think most of my friends know you as is a paleontologist at the Natural History Museum.
Right, yes. And I am that, certainly. It's one of the hats I wear. Yeah, I suppose, kind of in the short version, I spend a lot of time taking apart dead things so I can try to put other dead things back together. That's kind of what it boils down to. So less glibly, I'm interested in performance and biomechanics of fossil animals. You have to use modern animals to do that. And because there's a lot of anatomy involved, I know anatomy, and so I teach human anatomy. It's my sort of bread and butter as a professor at USC. But I am also a Natural History Museum paleontologist, and I like to spend as much of my time as possible playing with dinosaurs and pterosaurs and other very dead things. So I work a little bit with freshly dead things, some with moderately freshly dead things, some with not at all freshly dead things. That's kind of the range. It really simplifies permissions for your work. Like, like IOCook and IB aren't involved because everything's already dead. It really helps.
And all the paperwork was already dealt with the higher ups, I'm sure.
Yeah, exactly.
I'm hoping.
Long since taken care of.
So speaking of, maybe we'll start with the freshly dead things, because this I just found out before we started talking. And apparently it's not terribly uncommon. I had Neil Shubin on the show previously, a couple of times actually, and we didn't really talk about gross anatomy except for a brief moment where we spoke about the opening of Your Inner Fish, the PBS special, based on the book, where he started with a human hand and kind of talked about some of the analogous structures in the human hand. But of course, we didn't get any deeper than that. Obviously, learning about human anatomy and human, like you said, biomechanics is very helpful in comparing to these other organisms, isn't it?
Yeah, no, it really does help, and it's kind of turning the normal state of affairs on their head in a way. So what often happens is where scientists or biologists are interested in, say, an application to human health, just for example. But the experiments they have in mind would be too invasive or not practical on human models, and so they work on a model system of some kind. So, fruit flies are a model system for genetics. Mice are a model system for just about anything. It sort of sucks to be a mouse sometimes.
Especially a bread mouse.
Especially a bread mouse in the lab,
Yeah.
We have all kinds of different model systems we use for things over the years. We even use like zebra finches or model system for understanding certain brain functions. But when it comes to anatomy, it's kind of the other way around. If you're going to study vertebrate anatomy, the vertebrate that we know the most about the anatomy of are humans. And since we have access to a fairly large amount of voluntarily given human material through various human body gift programs, and we have one at USC, for example, we actually have humans as the model system for understanding vertebrate anatomy. So if you want to be a good vertebrate anatomist, you usually study human anatomy first, is the one model system. It's like if you study flies first for genetics, kind of in a broad sense, and then from there you branch into other vertebrate systems that you might actually be more interested in, which is kind of the reverse order of how it works in other areas of biology.
And so your training had a lot to do with human anatomy, and then you made those comparisons to these other vertebrates, many of which are long gone. But what you do in your professorship is actually just teach pure human anatomy. You're not teaching comparative anatomy, right?
I'm not. I'm just teaching pure human anatomy. I teach essentially two courses. I teach clinical anatomy, so for medical students, first and second year medical students at the Keck School of Medicine, and I teach them basically throughout the academic year. It's technically split between multiple courses, but essentially it's just human anatomy for 9 months, off and on. Averages out to about a lab a week. And then I teach a pre-medical human gross anatomy course as well for undergraduates at USC, which is actually a partnership between Dorn Seif, the School of Art, Sciences, and Letters, and the Keck School of Medicine. So they come over and use our cadaver lab.
That's not very common, is it?
No, that's fairly rare.
Yeah, that's really
rare.
cool.
So I have 30 undergraduates each semester. I teach it twice a year, and they come in there. We've got actually there's more dead people than live people in the room at that point. Because we have 35 cadavers maximum on the floor. Usually 33 of the slots are taken.
That must be really competitive for the undergrads. I can't imagine that I can't imagine that 30 or less people want to get into that class. I'm sure there's hundreds of people trying to get into that class.
Oh, there are. The wait list starts now a year in advance, and it is about twice the length of the enrollment. I limit the course because of the amount of time and energy I have and the resources and that sort of thing.
Sure.
When we teach human anatomy for the medical students, it's 186 students in the room at a time, but there's 7 faculty as well as teaching assistants who are all co-teaching.
And how many students per cadaver?
So there are 6 of them on a donor.
Okay, and that's about typical.
That's pretty typical for a big program.
Medical school now.
Yeah, for a big medical school, that's pretty typical. The smaller schools might be able to get away 4, 5 to 6 is pretty typical for big programs, and most of the top programs are larger. So not all, but most. So we're fairly typical in that regard. So we have 6 on them on a body. We'll have 5 tables on any given day that we're in charge of, we being any individual faculty instructor. So I have 30 of them at a time. That's about as many as you can reasonably instruct in there. So when I run the undergrad course was just me, even though I now have a whole room of cadavers, I still can't keep track of more than about 30 students at a time.
And how cool for those undergrads, because in a way they get more kind of one-on-one time with the cadavers than even the medical students. You have so many bodies there, and there's so many fewer students.
Yes, yeah,
it's awesome.
Yeah, you normally hear about teacher-student ratios. Yeah. We have cadaver-student ratios, which is now I say it kind of creepy actually, but
that's why I think it's awesome.
People. That's why I think it's awesome too. It's not creepy to me. I'm just trying my hardest to imagine what it'd be like to be in someone else's head that's less weird than mine.
Sure, no, that's fair.
Which is a struggle because I have been of this mind since I was very little. I declared I wanted to be a paleontologist at age 4. So
I love that. But you probably at age 4 weren't like, and I'd also love to teach gross anatomy to medical students using dead bodies.
Yeah, I would have gone through a lot of therapy if I had said that at that age. I was already in the habit of trying to catch things that most people would avoid and bringing them into the house and being told that I had to take them back outside. That was a constant cycle every weekend when I was a kid.
Speaking of randomly, yesterday, my boyfriend and I are coming home from a shopping trip, and there is a California striped racer, a large snake, on our front porch. Trying to climb up the door frame, and his tail is like slipping into the house underneath the front door. I got a picture. He was really fast. It's a type of whip snake, so they're super fast. And I posted it online, and people were freaking out. Like, don't let him in your house.
It's like, what's he going to do? Like, the dog might eat him.
Yeah,
exactly. Don't let him in your
exactly.
house. The dog might kill him. That would be unfortunate.
Unfortunately, my dog is not a very good hunter, so he'd probably just have my dog backed into a corner.
The dog would be barking at it.
Yeah. He's
It
just sleeping at our feet right now. It's actually quite adorable.
We found some cool snakes out night herping actually in the field. So you might wonder what do your typical paleontologists do after a day of finding dinosaurs and excavating jackets and things. Well, most of them would sit around the campfire, just drink beer and tell stories.
Sure.
We do that for about an hour, then we get bored. And then so we put on our headlamps and go out and walk the desert roads and look for snakes.
Nice.
And we managed to nab a pretty good sized prairie rattlesnake. Which was cute.
Gosh, how scary.
Oh, no, it's no problem. I carry a snake hook with me. It's not a big deal.
You just carry a snake hook around all the time.
Well, when we go on those walks, I do. Yeah, it's a folding field hook, so it's compact. You just unfold it.
I love that.
We got him off the road, so no one ran over him.
That's good.
But he was actually pretty chill. He it was one of those moments where he gave us a couple of warning rattles, and then I picked him up the hook, and he rattled once, and he was like, "Okay, I'd be dead by now if you were going to kill me. I'm not an idiot.
It's like, thanks for getting me off the road,
yeah,
man.
just over there. No, a little to the right. Thanks. Yeah, that's perfect."
And do you ever go out when you're in the field, especially when you're in the desert? Do you ever go out with UV lights looking for scorpions?
We have. We didn't the past season. I've done it before. We found a couple of scorpions. We don't see a lot out where we particularly are in New Mexico. We find some little guys. They're pretty cool. We do see some other cool invertebrates at night. We get a lot of Jerusalem crickets.
Oh, I love Jerusalem
which are
crickets.
Cool.
I met my first one last year at SciComm camp, the science communication camp that Jason Goldman and Sarah Curtis and I co-run. And it's new to me. I'm from Texas. Like, crickets in Texas don't look like that.
No, crickets in most places do not look like an alien invasion.
Like, it's weird. It's like it's an alien invasion of like fetal alien. They have these baby faces that are so creepy.
They're bizarre. They look like you mounted a baby head, like a human fetal head, onto a giant cricket body, and they just truck along. And they're pretty cool.
Yeah, I held one in my hand so that people could take pictures, and it was like trying to burrow into my hand. I was proud of myself for I'm not the biggest entomologist, so I was definitely proud of myself around all my ento friends, and they were like, "You can hold it," and I was like, "Okay, I'm not scared at all."
I don't mind it's trying to bury through my palm.
Not at all. I am totally not free. I'm just trying to look cool in front of everybody.
That sounds like you succeeded. Yeah. No, they're really cool. We see them. We saw a lot of camel spiders, which of course are not true spiders, but they're cool animals, cool arachnids. We also during the day see velvet ants.
Oh, wow.
Which are fun. And of course, being the sarcastic type that I am, when I was trucking through camp, we were making dinner, and one comes through and we go, "Oh, it's a shih tzu," because they're the beautiful little fuzzy, bright colored wonderful little animals. And she's coming through, and I sarcastically said, "Oh, someone pet her." And one of the students was like, "Oh, okay." I was like, No. I'm kidding. And she's like, "What? It looks cute and fuzzy." I said, "Yes, their nickname is Cow Killer, and they've earned that. Not by actually killing cows, but you certainly will wish you were dead if they. I don't know if you've ever seen one of them actually extend the stinger, the modified ovipositor. Mm-hmm. It's prehensile. Oh, God. It's incredibly long. It's this prehensile needle that pops out of the back of this thing and flexes around. So for those who are listening, just so you know, so velvet ants are these, look like beautiful, fluffy, red and black giant ants that you'll see walking around the desert. But actually, they are the female of a female wingless form of a wasp. So the males fly and have wings, and the females don't have wings, and they walk around, and because they're walking around and they're fuzzy, sometimes people think they'd be cute to pet them. But they pack a wallop. They have a very, very powerful sting. If you leave them alone, though, you can get very close to them, and I mean, we got our cameras right down on it, and they don't care.
Yeah, just probably best not to handle them.
That's not
you're
to handle
a professional.
Them. Yeah, I don't want to actually pick them up.
Yeah.
But they're pretty easy. You can scoop them up in a container pretty easily
cool.
and show them to students, and they just kind of truck around the container until you put them back down.
Well, man, if I was a paleo student, I would want to be out in the field with you. You have all these and I do entomology, and I do herpetology, and all of these things see a dead body lying on the side of the road, I could cut it up for you and show you what's going on.
Yeah, that one we might want to call the authorities first. Maybe they show up. They're like,
Probably.
"Why is it cut in half?" It was that way when I found it.
I was just really curious.
So
I'm trying to help.
I'm just trying to help you. You must have a really sick person on your hands. You should go find them.
I think he has some medical training.
Yeah, but I think that a little bit that's my old zookeeper days coming back into play.
How long were you at a zoo?
6 years, six and a half
Wow.
years.
Which zoo?
Originally the Maryland Zoo in Baltimore. Sorry. I tripped up there because it was originally called the Baltimore Zoo, which is what it was called when I was there. It's now called the Maryland Zoo in Baltimore. It's still a little weird for me to call it that. And I also worked in the National Aquarium in Baltimore.
Very cool. And this was after all of your training, after paleo training?
No, this was more or less before. So I had an interest in paleontology. This was before formal training. I started as an intern when I was 12. The curator liked me enough that she let me lie about my age and said I was 13.
Hilarious.
So I could start.
You could work at 13 then?
You could be a volunteer at 13.
Aww.
And at the time, any volunteer, if they got permission from the curator, could be a volunteer in animal husbandry.
Oh, cool.
Nowadays, they wouldn't do that. They would let them let them work as an educator, but they wouldn't put them in husbandry until later. But at the time, you could. So you're supposed to be 13 with permission. I was 12. We pretended not to know that, or she pretended not to know that. I started working there. I was an intern for a while, and then I got a paid position at the National Aquarium. So that was total up until just before I was 19, I guess.
Oh, so it was actually before college.
It was before and just into college.
Very cool. And is that what inspired you to want to get into, I'm assuming, biology, zoology? What did you actually study for your undergrad?
Undergraduate was just a general biology degree, but I loaded up on a lot of evolutionary biology, bio, as we like to say the slang. We're trying to be cool and we fail miserably. But yeah, a lot of bio, a lot of ecology, but a lot of zoology and such as well. But I did a bunch of genetics, everything else, just sort of gobbled it all up. I tacked on a couple of years for a master's at UVA as well. So by the end of that 6-year term, I had pretty much taken every biology course they had.
I love that. When I was younger and I was studying psych and bio, I ultimately went the neuro route. But there was a time, I'm obsessed with dinosaurs as just like one of those, I never grew out of 3-year-old Cara. And I've always been a big fan, as you can tell, looking around my office. And there was a time when I was like, okay, I have an undergrad degree in psych. I have a master's in bio. Maybe I want to go and get a PhD or like work in paleo in some way. And at the time doing research, I kept running up against this sticking point for me, which was that I had no geology. And it seemed like so many paleo programs were born out of geo or earth sciences. I think it's so cool that you were able to make this paleo career coming from biology.
And it's becoming increasingly common. Actually, if you go to the meetings now, what you find is there's a lot of biologists and there's a lot of geologists, both. But biologists are starting to outnumber the geologists at a lot of the vertebrate paleontology meetings. Not so much the invertebrate paleontology meetings, but at vertebrate paleontology conferences, if we assume that that's a decent sampling of the actual employment, then I'd say that probably half or more than half of them come from a biology background. Now, you still need to get some geo in there, especially if you're going to do field work. So I have some sedimentary geology in particular training, but not a lot. I mean, say at graduate level, but still not a lot.
So you kind of did it once you decided to go paleo. Yeah. You boned up on everything you were missing there.
That was about right. Yeah,
gotcha.
Exactly. That's about right. So there's different paths now, and I think in my case, the thing that's most unusual is that I'm sort of half theoretician, half field scientist. So you're getting increasing numbers of individuals that are traditional field paleontologists that have a biology background rather than just a geology one or a combined background. And you also get some that work as experimental biologists with a deep time interest, which would be sort of almost like that, sort of like some Neil Shubin, his kind of take on it, sort of evolutionary development kinds of folks, stuff like that. There just aren't a lot of theoreticians in general, actually, in paleontology, and the ones that there are, I'm one of the very few that also does traditional field work the other part of the time.
Gotcha. So they're usually kept pretty separate in that way.
And they are, and not on purpose or anything. It's just has kind of evolved that way.
Time consuming. I'm assuming, you got to stretch yourself pretty thin to be able to do all these different things. And you've got to be dedicated to, you got to be somebody who can wear a lot of hats and who likes to wear a lot of different hats.
Yeah.
Some people don't.
And some people don't.
Yeah.
And paleontology has, it was a long, slow slog for it kind of entering the modern era, becoming a more integrated field in a lot of ways. It was an old guard geologist field work, old boys club kind of field for a long time.
Yeah.
So it's not just that biologists started getting on the game. Women are now much more represented, for example, in paleontology, and that happened very quickly and also very recently. It's still a little heavy on the Caucasian side, but you are definitely starting to get particularly an increased international contingent. So it used to be, and by international, what I mean is outside Western Europe and the U.S.
Sure.
So those areas. So there was
South America, Asia.
South America is huge in paleontology now. The East Asian paleontology work is superb, and they've got a lot of great scientists now working in the field. Some wonderful Japanese scientists, Chinese scientists, Korean scientists working in the field. Russia's gotten kind of back into it. They kind of were part of the old guard, and they kind of fell out for a while. Now there's some really great vertebrate paleontologists working out of Russia again, and African scientists, some really superb guys in Madagascar, for example. So it's Tanzania.
Very cool. I wonder if that's why when I first did, that like minor amount of investigation into different degree programs, I grew up in Texas. I'm a Southern girl, and I wonder if just these Southern programs were much more earth science focused. Whereas you mentioned that some of these places where you learned a lot of comparative anatomy were like East Coast institutions.
Yeah, that's exactly right. And in fact, Texas, more than any of the others, is geo-oriented. Well, University of Texas Austin has one of the top paleontology programs in the country. It's in their School of Geosciences, which is, I think, considered the top geoscience program in the nation, or at least it competes for that top. I mean, the rankings are all a little bit subjective, but it's consistently considered to be a top program. But that means that they have a real interest in kind of maintaining that geo-focused paleo track. So I think you're right that it's the South as a whole, but Texas in particular really trains paleontologists out of geology. If you get into the Northeast, they train them mostly out of biology. And if you're like mid-Atlantic, where I was, it's kind of split half and half. And if you come to the West Coast, it's also mostly out of biology. So most of the paleontology programs out of West Coast schools, UCal schools, for example, Berkeley, it's biology-based. UCLA, biology-based, primarily at least.
That's fascinating.
USC, we're all biology-based. There's a bunch of us now at USC that are all paleontologists, and we're all in the School of Medicine.
And do you do any work in, obviously you do your paleo work at the museum, you do your paleo work in the field, and you, as a professor, you teach gross anatomy. Do you do any paleo work at USC also?
I do. I mean, basically, I have sort of the traditional, it's a traditional full-time professor kind of gig, right? So I've got a research role, which they call scholarship because it sounds fancier. It basically means go discover stuff and learn about it and write about it. That's really what it boils down to. I like to joke that I'm really just a professional writer and I have to do good science in order to have things to write about, basically. So, but anyway, so that's the research angle. And then there's the teaching angle. And there's a little bit of what they call the service angle, which is go sit on boring committees and, try not to hit your head on the desk too hard. For the most part. Although I work a little bit for my service actually in admissions. I actually interview students. And that's fun. I really like that, actually.
That must be fascinating.
Partly because the admissions dean is awesome, but also just because it's cool to do.
Yeah.
So mostly I split my time between research and teaching. And my teaching is human gross anatomy, and my research is mostly paleontology and biomechanics and motion performance of fossil and living animals. And I don't have a traditional lab at USC for that. My lab is basically the collections at the Natural History Museum, where I have this joint appointment. So,
which is literally across the street.
The street. So that's how I work that. So, but when I'm doing that work, it's technically as a representative of USC as well. So So I am representing both the museum and USC when I go out to the field. I'm representing both of them when I publish papers on either the theory or the fieldwork aspects of my research. And when I take students into the field with me, it's USC students.
Mm-hmm. And so you split your time between teaching and research, and then you split your research time between being in the field and actually doing the theoretical work on, as you mentioned, biomechanics. So the way that these organisms, the way that we would theorize based on the fossil evidence we have of how they would have moved when they were alive.
Yeah, exactly. So, and the reason I describe myself as a theoretician in kind of the old school sense is that I actually work in that kind of context. So I take animals and basically turn them into math. That's essentially, in a nutshell, I do. I spend a lot of time on a whiteboard rather than in front of a microscope, as it were. And what I try to do with that aspect of my work, and sometimes successfully do, like all research is a fair bit of trial and error. But what I work on is developing predictive models, which are basically series of equations, basically families of equations that should predict how performance works in animals of various kinds. And this performance is usually motion performance.
And so this is like when you watch a show on Discovery Channel and they're like, how intense would the bite of Megalodon have been or something? And it's like you can do these kinds of calculations to try to get within some sort of reasonable error how strong their bite would have been based on both fossil evidence, but also based on like analogs to modern living organisms.
Right. And when you're doing these sorts of, that's exactly right. And when you're doing these sort of quantitative sorts of models that I do, one of the things you do is good practice is to validate the model on living things. In other words, if I say, oh, well, I think this predicts based on these 5 shape variables of the head, for example, how strong bite force would be, then it should work when I apply it to living sharks for which we've measured bite force. Yeah. Right. And then you look to see if it does. And of course, it won't be exact, but if you get really close repeatedly, you go, okay, then it probably works on fossil things. And then you have to ask yourself, okay, do I have some way then of validating that it's working on the fossil animals? So, well, that's a little more difficult. So what you do there is you then use the models to make predictions about certain aspects of anatomy you would expect to see, say certain correlations, for example, you might expect to see in the fossil record that, okay, well, if I'm right about this, then an animal that has an extended moment arm here in the form of this kind of bony flange should also have a joint reinforcement here. Okay, if I look in the fossil record, do I tend to see that does typically line up? Does that generally line up? And then if it does, then that's the last sort of level of validation. And then from there, of course, you'll never know for certain, but you feel, okay, well, it works on living things, makes good predictions there that I can truly validate. It makes predictions about fossil anatomy that I do see. Therefore, this is my best estimate of what the performance would be this animal, and I think it bit about this hard.
So obviously that raises some questions for me coming from the outside, because it seems like, okay, let's say I'm a paleontologist who studies extinct sharks. Well, I have these living analogs of these extinct sharks, and some things are different and some things changed with evolution, but some things are conserved really well. If you're studying something like pterosaurs, for example, where there's no living relative, there's no analog, like you're literally guessing how they walked and how they did, maybe not guessing, but making these observations and trying to figure that out must be a little tougher, huh?
Yes. So I like a challenge.
Yeah.
I'm also clearly not averse to heated debate because I work on multiple groups of fossil animals that basically of the 3 groups of fossil vertebrates that probably have the most vicious debates amongst their workers, I work on 2 of them.
And what would those 3 be?
The 3 would be hominids.
Okay,
so that one's pretty obvious. Hominids, pterosaurs, and theropod dinosaurs are probably the top 3. And I work on the number 2 and number 3 in that list. So pterosaurs are particularly difficult because we have no living representatives. And we don't even have anything that's terribly closely related. I mean,
yeah, like with theropods, at least we have birds, which are similar to one group of theropods that continue to evolve. I mean, it's very far removed at this point, but at least we have them.
At least we have them, yeah. I mean, they're just really weird derived theropods. Whereas, I mean, birds and crocs are the closest living relatives of pterosaurs, and
they're so nothing like them.
And they're really not that much like them.
Because birds are similar to them in the sense that they go back to the same common ancestor of pterosaurs and theropods, right?
Right. So there would be a common ancestor of dinosaurs and pterosaurs, assuming that we have the phylogeny more or less correct. pterosaurs have been a little bit of an enigma in that regard, which is even more difficult. But we call that group Ornithodira. Assuming the Ornithodira hypothesis is correct, then you have that common ancestor. But that's the common ancestor of pterosaurs and all dinosaurs. So a pterosaur was no more closely related to a bird than it was to, say, Triceratops.
Yeah.
The fact that a bird also happens to fly is essentially a biological coincidence.
That's what we refer to as convergent evolution,
Yes.
right? It's like two totally different flight styles, different flight patterns, totally evolved separately, the same way that a bat wing and a bird wing would have.
Right.
And you use things like bats to look at pterosaur flight. You use things like like anything that can fly. You're like, what parts of it are similar and what parts aren't?
Absolutely. So I've used birds, I've used bats, I've even looked at aircraft design, and although it's kind of fun because now these days we're starting to see a little bit of possible flipping on that. I have talked to some aircraft designers who are now interested in inspiration
that biomimicry
from pterosaurs, which is kind of cool.
Cool.
And if that goes forward, they'll be I think the first time that there's been a tech transfer from a fossil group.
Wow.
Which is kind of cool. We've been doing some biomimicry stuff on living groups for a while, but that will actually be a tech transfer from a group of organisms that has been dead since long before there were any humans at all.
Which means that the theory is really important for that kind of tech transfer.
Right.
Yeah.
Right. And actually, that's really where the tech transfer comes from. It isn't so much that they want to make a pterosaur. It's the things that you develop by trying to solve pterosaur problems leads down different pathways you might not have otherwise stumbled upon that gives you ideas that would be interesting for other things.
So obviously one of the big limitations of doing this kind of theoretical work where you're trying to figure out and sort of recreate so that you can further understand the biomechanics of this long dead organism. One is that there's no real analog today. And two would be that did I read this correctly? Only 150 specimens or species?
Species.
Okay, good. I was like, 150 different known species, which is significantly smaller than the number of known dinosaur species, for example.
It is. And it's largely because flying animals have a knack for dying in places where you don't get fossils from them.
And is it also harder for them to fossilize? Is it just because of where they tend to die?
It's a bit of both. There is an issue in that the later pterosaurs in particular, so some sort of mid to late Cretaceous, even early Cretaceous forms, overwhelmingly have a great deal of what we call pneumaticity. So that is, they have a lot of air sacs in their bodies, and those even go into the skeleton. Modern birds do this as well. Those types of skeletons tend to have very thin walls on the bones, thin layers of cortical bone. They're actually very strong, stiff skeletons when the animal's alive, because you have these large diameter, thin-walled bones that makes them very stiff in bending and torsion, so twisting and bending forces they do fine with. And in terms of local impacts, they're blunted out by all the soft tissue that's on the animal. So
it's like having carbon fiber instead of steel.
In a sense, yeah. Yeah, it has a very high strength to weight ratio, exactly. But once you strip all the soft tissue off and the bones dried out, remember, half of your bone mass is water. So, and there's also a lot of protein in there. Once all that's gone, it's just a desiccated skeleton. It's very brittle and also very prone to crumpling from local impacts. You put weights on it and it starts to just sort of crumple down. So they had skeletons that were very robust in life, but very fragile in death, basically.
Which is not doing you any favors.
Which is not doing me any favors or anyone else who works on pterosaurs. Yeah. So we end up with a lot of roadkill specimens, so things that are flattened, which of course removes a lot of information, and we end up with a lot of shards that we can't do much with. And of course, we know that there will be a lot of them that are past the shard stage, that is, they're just completely obliterated and we never found them. Obviously, we don't know how many of those are for sort of self-defining reasons, but but we know we lose a lot of them. You know, the fossil record of birds is also a little bit sparse considering how many birds there are now. And there's no reason to think that there's over like 10,000 species of birds now. There's no reason to think that suddenly just happened in the last couple of million years or something. They've probably been diverse for a while, but from a lot of time periods, we only have, a few dozen or a couple hundred, species of birds, depending on exactly what you're talking about over their 150 million year duration. And that's just because of preservational artifacts and environments and things. A lot of the environments that have the most biodiversity in general, and particularly biodiversity in small flying animals, for example, today, don't leave good fossil records. You imagine that you're going to be a future paleontologist. By future, I mean, let's say 10 million years from now.
Okay.
And you're trying to reconstruct our time period. You'll have a very good fossil record of coral reefs. You'll have a very poor record of tropical rainforests. Mm. So you'll know that, for example, the Caribbean reefs existed, and you might have a good idea the Great Barrier Reef was there, but you will have no idea that the Amazon was.
Wow. And that's just because of the way that the fossils would have preserved based on all of the different weather patterns and ecological kind of things happening in those areas.
Exactly. It's just the environment of those places. So shallow, warm water that's alkaline, which is, most of your shallow ocean or coastal oceans sources, preserve fossils pretty well, especially shells and things of that nature. Mm-hmm. And you kind of, a lot of those animals have hard parts. So even the invertebrates have hard skeletons, either exoskeletons or shells of some kind. And they also have high sedimentation rates often. So you're putting in a lot of fine sediment. Some of that sediment's actually crushed up coral and shells. So some of it's essentially going to become limestone. Others could be sand that's washed in. But one way or the other, you have a lot of fine sediments in an aquatic environment that's very good at preserving things for long periods of time and leading to fossilization. On the other hand, as soon as something hits the forest floor in the Amazon, it starts getting scavenged.
Yeah.
And there's going to be almost nothing left of it in a week, much less than 10 million years.
That's so interesting. And so really, you know so much about the fossils that you have to work with just because they're fossilized.
Yes.
You already right there have a wealth of information because they happen to be able to be fossilized.
That's right. And we can say something about the conditions that they were in based on the surrounding rocks, but we already have a bit of a hunch just based on the fact that they are fossils in the first place. As soon as you find a lot of fossils in a spot, you start thinking, for example, there was probably water. Mm-hmm. Not always the case. You can get fossilization by, say, burial via, say, a sandstorm and fine-grained sands in a desert environment, but often, even in dry environments, it's a flash flood, or a floodplain with seasonal rain or something. Water tends to be involved. Again, not always, but very often is. So right off the bat, you start seeing lots of fossils. You're thinking, let me look at the sediment a little more closely because it's likely this was a lake. Gotcha. And the reason that these things are being preserved here is because of the lake. One of the best records we have of forest living animals from relatively deep time is actually some of the stuff from northeastern China. That's where you get a lot of the famous feathered dinosaur specimens and such. And the reason why you're getting a forest community that's preserved there is because there were lakes within the forest, a lot of them, and they get preserved in these relatively low oxygen content lakes. Mm-hmm. And the low oxygen helps prevent decay, at least at the bottom of the lake. And so these things were falling into the lakes. One of the reasons why we have such a good record of flying animals from the spots is that flying animals go over lakes and then sometimes die over lakes.
That's where they feed.
That's where they feed. And so, and at least they can cross them. Mm-hmm. So we have a particularly good record not only of a forest community there, which is rare, but it's particularly enriched in things like Mesozoic birds.
Makes sense. Yeah. I think back to the one paleo class that I took in community college when I was getting my freshman year and my senior year of high school done at the same time. And I took a paleo class. It was actually called Dinosaurs in all capital letters with an exclamation point in the course guide.
Wow. You know it's going to be a good course when it's got an exclamation point at the end.
You know it. And our textbook was called Lone Star Dinosaurs. It was a very Texas course. And I remember specifically learning so much about the dinosaurs that were very famous and the places where I grew up by, like Dinosaur Valley State Park, like Acrocanthosaurus was a big one. And it was aquatic. Like almost all of Texas was aquatic. There were so many, it was like an ocean environment. And I think that that's why we had our special dinosaurs that we could remember so dearly. And there's a bowl of fossils literally on the counter behind you that we would just pick on the side of the freeway. And they're all ammonites and aquatic fossils that were just basically at one point in time, it was water.
Yep, exactly. There's been, so good portions of Texas have been underwater multiple times throughout time, and including the Mesozoic. And so you guys were actually on the coastal shelf at that point, basically. And there's been a shallow seaway, actually, for much of the late Cretaceous. There was a shallow, and mid-Cretaceous, there was a shallow seaway that cut North America in half.
Oh, wow.
So where we are in LA would be part of Appalachia, which would have been underwater at the time.
Crazy.
So we would have been underwater on the West Coast, but there would have been an East Coast to Laramide as well. And then there's Appalachia on the eastern side, separated by this Western Tier Seaway. So that's why Kansas, its Cretaceous fossil record is almost all marine.
It's so
even though it's landlocked now.
Yeah.
So but these marine records tend to be a lot richer than the terrestrial ones. You just get, so we even have We even have terrestrial fossils that sometimes get washed out from the coast and end up being preserved there because the preservational probability is so much better underwater. So you get some beachcombing land animal and it ends up as a fossil in the ocean. That, of course, doesn't mean it was aquatic.
Yeah.
You didn't see a lot of truly aquatic stuff alongside it, which is kind of funny. We have a number of dinosaurs, actually, that were preserved that way, got washed out to sea somehow.
Oh, interesting.
Yeah, probably died on a river or something, got washed out to delta, picked at by ocean-going pterosaurs for a little bit or something, and sank to the bottom. And and they're rare, but they do happen.
That's
the fact
crazy.
that you don't get the reverse, right? We know aquatic animals do occasionally get beached on land, but you just don't see them as fossils very often.
Yeah, and you wouldn't have a whale that's like crazy inland.
Yeah, it's not gonna be crazy
right
inland.
there.
It's gonna be right there, and it's still, it's in a way that the reverse scenario is not as likely to form a good fossil as the other way
first.
around.
Yeah. It's like I mentioned, Acrocanthosaurus. Obviously, this is a huge theropod. This is not like an aquatic animal.
No,
but it would have been
washed out
feeding.
there.
It would have been washed out, whatever. And there's some really famous tracks there in Dinosaur Valley, like I guess on a riverbed where those tracks were able to preserve really well, and you can actually walk alongside them and. It's so cool.
I like your three-toed
you like that?
by the way.
I'm remembering going there as a kid and being really, really amazed. Took some good pictures. It's so cool when you have things like that close to home. And the funny thing is, here in the States, there's so much good paleo. I feel like almost anybody has something brilliant like that close to home. They just need to get out there, go to your local museum, go to your local field, area, and figure out what your hometown treasures are.
Absolutely. No, there's areas, for example, upstate New York. You can drive a short distance out of Buffalo, for example. There are trilobites.
That's crazy.
In the road cuts and stuff, yeah.
And you can see the KT boundary in parts of New York, can't you?
Yeah.
That's awesome. There's like some cool research that's been done out there specifically because you can see that in the rock. That's amazing. This is so fun. Okay, so I didn't even mention yet, but pterosaurs.
Yes.
There's an exhibit at the Museum of Natural History of Los Angeles County right now, and it's I guess, is it a traveling exhibit from the Museum of Natural History in New York?
That's right.
Okay.
Yeah.
Or American Museum.
American Museum. Yes. So it was launched at the American Museum of Natural History in New York City, and I was the lead consultant on the exhibit. The co-curators are Alex Kellner and Mark Norell. And Mark, of course, is in-house at the American Museum. Alex Kellner is from Brazil. He's in Rio de Janeiro, so he's fighting Olympics traffic right now on a daily basis, which I imagine is making getting to and from work a little bit extra difficult. But I hope he's having a good time with it. And they're great guys and top-notch paleontologists. Alex is a pterosaur specialist. He has published on other things, but he works probably 90% of what he does is on pterosaurs, and he's a world-renowned specialist in them. Mark works more on dinosaurs than pterosaurs, but he has worked on some pterosaurs as well, and he was the host curator there in New York. But they brought me on as lead consultant because neither of them really works on the biomechanics of flight. And the subline or subtitle on the exhibit is Flight in the Age of Dinosaurs.
Yep.
They wanted to go with a flight heavy route on it, flight mechanics heavy route, and basically Mark brought in Alex is a top-notch pterosaur guy and someone who actually had a connection with the American Museum. Alex had been a postdoc in the American Museum.
Oh, cool.
Which is pretty cool. And actually in a funny little caveat I found out about, apparently, so Mark Norell has what's been argued is the best office in New York.
What?
And Alex, when he was a postdoc, had the same office.
Oh, how funny.
So Mark moved into it years later when they got hired as a curator there. After, I guess, Alex had.
And why
out.
is that? Is it the view of Central Park? What?
So if you've ever been to the American Museum, it has on the corners these what look like giant castle turrets, and it's in one of the turrets, and it covers the entire floor of the turret. So it's a nearly 360-degree window view, looking out on the Central Park on one side, and then out onto like parts of the museum and grounds on the other 200-something degrees or whatever. The only place where it's connected to the building is basically the doorway, so it's just glass all the way around.
I want to go to there.
Yes.
That's amazing.
It's amazing. And you go in there, and he's, unlike myself, actually, Mark and I bonded over this, he's an orchid enthusiast. So he has orchids growing all the way around because he gets sunlight all the way around. And then, so it's like a tropical orchid paradise along the windows. And then, of course, just inside that is trays of fossils most days that he's working on. It's pretty cool.
Are orchids ancient?
Orchids are not terribly ancient. It depends a little bit when you consider to be ancient. They do not harken back to the Mesozoic. So that's not an interest he got into because of his work on Mesozoic vertebrates. It's just something he just likes growing.
I love orchids too. How could you not? They're gorgeous.
They're awesome.
The biodiversity of orchids is so apparent You know what I mean? They flourish in the most bizarre ways, different colors, different shapes, and they're just interesting plants.
Oh, they're very cool plants. And I have over 40 species in my apartment.
Wow.
And that puts it at 0.01% or something of the modern diversity, since there's I think 13,000 recognized species at last check.
And so wait, how do you keep these alive if you're always out in the field? Because I can't keep one alive and I'm home most of the time.
You know what kills most orchids?
Overwatering them.
Yeah. Yeah. In fact, just in general, messing with them too much.
I tend to just let them die slowly. That's usually, I'll buy an orchid, it'll be beautiful, and then I'm like, I'm just not going to touch it. I might periodically, if it starts to look sad, mist it with a spray bottle, and then it just slowly will die. And I'll be like, that was a good run, 4 months of an orchid.
Dude, well, 4 months is better than a lot of people
That's
do.
Good.
But yeah, you read up, you choose carefully. With that many species, not all of them need watering on a super regular basis, and that sort of thing. I've set up I actually have some of them growing somewhat in a what we call a semi-hydroponic setup.
Okay. Yeah.
And so you fill up trays of water and it kind of wicks up and you just leave and you come back a month
Nice.
later and there's still got water in the reservoir. So there's that option. I have some that are just very, very dry tolerant. I do have some growing as mounts. I have some that are actually growing on branches and
That's so
bark and
cool.
stuff. So more like they would in the wild, which is kind of fun. But those were, I specifically picked ones that were very drought tolerant, so I could leave them for a while without being watered and they'd be okay.
I'm having this image right now of Robin Williams being Oliver Sacks, except his name was Sayers in the movie when they redid Awakenings as a film. And he's going back to his apartment and his refrigerator is just full of plant specimens.
Yes.
Is this what your apartment is like?
The one part of the apartment does look a bit like that.
You are married, though.
I am married.
Which is good, because he was very sad, and it was definitely
Yes.
just him in the film.
Yes, and of course, and my wife does does help care for them when I'm gone. But she's a physician, has long hours, and so they still need to be somewhat self-sufficient. And I got married relatively recently, and there was definitely a time when I had orchids and didn't have anyone else at home. So I've created a system that makes them pretty self-sustaining. The same goes for my pets. Actually, there's a reason all of my pets are things that can be fed once every couple of weeks.
Oh, so do you have a lot of herp pets?
Yes.
Yeah.
Exactly.
Gotcha.
Yeah.
And it's so much fun to feed a snake, isn't it?
Oh yeah.
Do yours eat live prey?
No, they're all frozen thawed. I don't want to deal with that.
It's a pain.
It's a pain in the butt, and it's just messy,
It's always fun though to get a group of people around to watch a good feeding.
Yeah, it's fun. Yeah, it is funny though. You get people get so excited. They're like, "Wow, why don't you feed it live stuff? They want to see it kill things." I'm like, look, I worked for 6.5 years in a major zoo and a major aquarium in the reptile divisions, reptile and amphibians primarily, a little bit of birds as well. I said, I had to deal with so many stubborn feeders that would only eat live prey or eat a certain kind of live prey, and all the stupid tricks we had to pull in order to get them to eat. You know how much of a relief it is that I can just thaw out a frozen rat and just throw it in front of my blood python and it will just eat it and I don't have to worry. That's wonderful. Why would I make this more complicated? I spent years having to deal with complicated because I had no other choice.
That's true. There are a lot of people who have snakes where they try to feed them live prey and the snakes will fuck with it until it dies and then it won't eat it because it's dead.
Right.
And you're like, what?
And quite frankly too, predators are efficient for the most part in killing the prey. I mean, they do tend, that they're not adapted to be like murder machines. They're adapted to eat. Nonetheless, I have seen enough horrible things happen to live rodents in feeding contexts that I don't really need to play that game. There is a certain amount of ensuring that things are humane that goes into the whole. I've watched a carpet python corkscrew a live rat.
Whoa.
To the point where its posterior half was 180 degrees from its anterior, so it just snapped the spine and torsioned it. And
I hope he ate it after.
Oh, he ate it after
that.
Good. And
but yes, that can't have felt good.
Yeah, I mean, I'm sure it was dead seconds after that happened, but not a fraction of a second.
Yeah,
seconds plural.
Yeah, and especially if you've done
awful.
Lab work, if you've done research, I did a lot of research with mice. That was our main experimental animal. And you do so much to ensure that the work that you do is humane. I had to sacrifice a mouse a week in my lab for many years. And all of the work that you're going to do, you make sure that the mouse can't feel anything, that it immediately goes to sleep, that it doesn't, experience any of the negative side effects there. So it's, I guess, a little bit morbid.
Yeah. Oh, I mean, there was something
to have
very,
like a Colosseum situation going on in your
Well, I can understand it too,
snake
because
tank.
it is really interesting to watch how predators operate. And they are efficient hunters. And most of the time, they do dispatch their prey very quickly. And it is essentially humane. But there is that risk that it's going to be a little slower, a little more painful than you were expecting it to be, because the snake doesn't care about being humane. It cares about efficiency because because it's actually eating prey that is potentially dangerous. I mean, at snake size, a rat is a large, fast animal with knives attached to its face. So you're killing it quickly for necessity. But if you happen to get a weird grip on it that one day that just happens to be a little bit awful, it's not like it's going to be, I can't do it. There's rules, it changed its grip. It's just that rat's going to die more painfully than the last one. And, if things are already dead, and I can just rest a little easier at night.
Yeah.
And mostly, honestly, it's like I said, it's just less complicated. I can buy them in bulk. I've got enough animals that I can buy the
Keep them in the freezer.
Keep them in the freezer, right?
Yeah.
I buy bulk rats, bulk mice, keep them in the freezer. My turtle eats a ton of them, so that's handy.
It makes me wonder, too, how much, obviously, we think of different kinds of organisms of having different levels, I guess, of domestication. When we talk about sort of artificial selection, obviously my dog is like a pure product of artificial selection, but a lot of reptiles aren't. We think of them as live captive, or I should say wild captive organisms, but it does make you wonder how much of this maybe sort of behavioral shift happens over the course of the life where you're feeding it frozen things. It's like, I don't have to work for my food much anymore. It's right there. It's ready for me. And I think that's why you sometimes will see these snakes, for example, that are fed a live organism and they don't do what they're supposed to do with it.
Sure. And actually a lot of reptiles that are kept as pets now are essentially domesticated organisms too. I mean, none of mine were wild collected. I don't have any wild collected.
So they've all
reptiles.
been bred at least multiple generations.
Yeah, and all of mine were born. Mine are all at least F2s, if you will. So they're all at least the grandchildren of wild caught animals, and in most cases, more generations than that. And yes, most of them are still pretty wild type, but you look at sort of the designer trend in like ball pythons, leopard geckos, bearded dragons. I would argue that some of the sort of top 5 most popular, most sort of custom engineered via selective breeding species are basically domesticated now.
Yeah.
They're not as derived from the wild type as a domestic dog is.
Sure, because that's been thousands, actually, of years of domestication, not just
But they're still
hundreds.
pretty removed. We have plenty of reptiles now that could not survive in the wild.
Sure.
We have leopard geckos that are different size, different shape, wild colors, and have never, it's been 5, 6, 7, 10 generations since one of them had to hunt really on its own, right? That's essentially a domestic animal. It's just in a much earlier stage of that domestication than a dog or even a domestic cat. But
so you keep doing it, maybe it'll get a floppy tail, start wagging its tail.
Yeah, so you never know. I mean, we certainly, I think we're going to eventually start to see. And we're already starting to see a little bit of it. I mean, there was a time when I first started working in animal husbandry, and of course, a lot of people I was working with owned various exotic reptiles and amphibians at home, and I had my own little collection as well. But that was a time when we were just kind of trying to figure it out. And these were still essentially wild animals you were keeping in your home. They were maybe first generation captive bred. Some of them might have been wild caught with a permit, whatever. And we were kind of trying to figure them out, and they weren't sort of customized at all. And there were a lot of species on the market, and a lot of them didn't do very well. And increasingly, it's getting funneled down to a smaller number of species that do well and have been essentially engineered. And I think what you're going to see pretty soon is other kinds of weird morphology being selected for other than just color. It's been mostly color and size.
Yeah,
so
but you
far.
might start
We've
seeing
dwarfed some of them.
things.
I think we're start seeing some weird shapes.
Yeah.
I don't think it'll be long before you start seeing people selecting for like shorter faces or bigger eyes to make them cuter.
Yep.
Things like that.
Because that's a natural progression, I think, for humans keeping these organisms as pets. It reminds us of babies, right? This was the word of the week on Skeptic's Guide a couple of weeks ago. I mentioned neoteny and pedomorphism. It makes me wonder, though, because I'm like a traditional pet owner in the sense of like, I love my dog because he's furry and he smells good and he snuggles up next to me and his fur feels good on my skin and he's very cuddly, and I can't cuddle with a reptile. What is it? Is it more like the curious fascination of watching them do their thing? Like, what is it that attracts people who keep reptiles to their pets?
That's a good question. So for me, I consider them to be kind of honored guests in my home that I make sure are well taken care of and are in the highest level of health. And in return, I get a certain amount of enjoyment watching them and understanding more about them and enjoying their biology and their behaviors.
So it's like a curious observer, kind of field biologist relationship with your pets.
To a large extent, yes. Now, mine are mostly handleable. I mean, I can take one of the snakes out, for example, and it'll sit in my lap while I watch TV if I want. I don't do that all often, but I can do that. It's kind of fun. I do also use my animals also double as education animals, so I do actually take them out on education trips to visit kids because they are all hand raised, multiple generation captive bred animals. They are all very, very gentle, very, very tame. For a lot of kids, that's one of in LA, for example, they've never seen a python, much less being able to touch one. So that's really cool for them. And you can talk about genetics. I have a couple of milk snakes, for example. One of them is a normal coloration animal. The other one is an albino. So you can talk a little bit, so I'm like, these are the same species, but they look really different. Why do they look really different? Well, one of them doesn't have black pigment. Why is that?
Also, this guy would not do well in the wild.
Yeah, exactly. No, but this one would not survive in the wild. You can talk a little about selection and evolution with them and that sort of thing, which is kind of cool. So they double a little bit as education animals for me personally, which is not normally the case, but since I'm a professor and biologist, obviously that has that angle. And it's just sort of it enriches the environment of my home.
Yeah, and of course, as somebody who's really interested in biomechanics, specifically you focus on flight, but I'm sure you focus on all sorts of different ways that the joints move and that the body moves and they eat, and you keep reptiles. And technically, dinosaurs and pterosaurs were reptiles.
Yeah. Oh, yeah. No, they were very much reptiles.
They were birdish in some ways too, but yeah.
Well, and birds are reptiles is what as
exactly.
well. Actually, if you do want to be technical about it, so really birds are reptiles as well. But in the more familiar sense, non-avian dinosaurs and pterosaurs were reptiles. There's a connection there. It would be cool to have flying animals at home as well, but rather impractical. And that's why I don't have anything that flies, even though I work on flight for a living. I opt instead to put out hummingbird feeders on the porch, and I attract little flying friends that way.
There you go.
And actually, I can get some pretty good high-speed video of them sometimes, which is kind of handy.
Yeah, that's fascinating. Watching hummingbirds fly is fascinating. Yeah, it's cool really, that we have the tools to be able to do that now, which we didn't, probably 20 years ago. You wouldn't be able to do that from your own home, except with like a pretty high price tag.
Yeah, exactly. You get a $10,000 camera now. It's just like, my smartphone takes pretty good video.
Seriously, it's really neat. Like the iNaturalist, I talked to on the podcast about iNaturalist when Leela Higgins was on, and of course I had this snake on my front porch. I text my friend Jason Goldman, can I get an ID on this? Or actually, I texted a big group of all my friends. He just came back to me first. And he's like, put it on iNaturalist and tag it Rascals. And it's so cool. I did that on my iPhone. I'm a citizen scientist the same way many of my friends are citizen scientists. And I used to work as a scientist, but I'm not a herpetologist. I don't work for the museum. I don't know any of, exactly what's going on. But I can take a picture of a cool living creature right outside my house and upload it to the internet, and people can learn from it.
Yep.
Yeah, really amazing.
Yeah, absolutely. I mean, it's funny actually. I sort of I like the term citizen science to some extent, but I also, to some extent, think it's sort of a misnomer in the sense that we're all citizen scientists.
Yeah.
And I would say, really what you're saying is, do you get paid to do scientific research or not?
Yes.
And even if the answer is that you do, you only typically get paid to do one kind of science. If you're doing any other kind of science, you are in that non-professional citizen science role in that moment anyway. I'm not an astronomer, but I still love the sky watch.
Me too. Yeah, I've got my telescope right there. And you've got the herpetology, you've got all of your orchids, but you don't get paid to do any of that.
No, of course not. Yeah. Yes, that's just me. That's just hobby science,
Yeah.
I think there's a bit of science in everybody, scientists in everybody, and I just like to try to nudge that out a little bit. Where I can manage, but modern tools are really, I think, really help people get involved in projects that are bigger than themselves. basically.
So, Mike, you know what I just realized? That we've been podcasting for a whole hour, and we've hardly talked about pterosaurs at all, which is fine.
Which is fine, but we can wind it back to pterosaurs.
Yeah, we can wind it back for a second before we go. You know, I first met you because you were on a panel that I moderated for Jurassic World when it came out. We did the museum did this kind of cool publicity thing where you could get a ticket to the museum and a ticket to the movie, and we were at LA Live, and then we had this great panel after. And I remember you had some real insights about some of the flying reptiles in the film.
Oh, yeah.
Maybe that's a good place to start, because I think a lot of people have heard of pterosaurs. They've heard of the term pterodactyl. They may have heard of different types. Maybe they've heard of, tell me if I'm pronouncing it right, Quetzalcoatlus?
Mm-hmm.
Yes. Which I think, was that the pterosaur that was in Jurassic World?
No, it did not appear.
Oh, it didn't? What were the huge ones in there?
And one of my comments was that they might as well have put it in. Well, that's kind of the funny thing. There are some big pterosaurs in that film by your sort of typical, probably observer standard, but nothing nearly as large as the largest flying animals that we actually know of. So it was a kind of a missed opportunity, was kind of my point. And I realize that it's a blockbuster film. I realize it's ultimately sort of a horror genre film. It's fine in that regard. I'm not looking for a particularly high level of accuracy. It doesn't mean that I'm not going to nitpick anyway, because I'm a paleontologist and I enjoy that. Everyone enjoys getting up on their soapbox, right? But I do think it was kind of a funny missed opportunity. There were a number of things about the pterosaurs in Jurassic World that I could criticize. The anatomy of them was actually pretty poor.
Really?
Which is interesting, because the anatomy of some of the other animals in the Jurassic Park franchise has been very good.
So it's almost like they really focused on dinosaurs and sort of just left those to be accessory decoration in the
Basically,
film.
I feel like they were kind of like an afterthought, yeah. But the other funny thing is, okay, it's a horror film, and you have a scene where the pterosaurs descend upon the crowd, and you picked Pteranodon, which is a moderately large pterosaur, and Dimorphodon, which is a really cool animal that they turned into some kind of horrifying gremlin sort of thing, which is not what it probably looked like in life at all. But so we'll say kind of Dimorphodon. I think that's what it was supposed to be. Sort of pseudo-dimorphodon. But they picked this thing, which is very interesting scientifically. But I mean, I just thought it was very strange. That's not an animal. Dimorphodon in particular is not an animal that's particularly famous to a broad audience.
Yeah, like they could have picked
Pteranodon is, yeah.
Yeah,
Pteranodon is, but isn't, which means someone did a Google search at some point. If they did that, they clearly could have and should have, and probably did, stumble upon things like Quetzalcoatlus. Now, I'm just curious. I'm going to maybe the listeners can decide which one of these is more horrifying. The Pteranodon and Dimorphodon group descending on people and kind of doing an Alfred Hitchcock the Birds thing, but poorly, including a couple of moments where they are very implausibly picking up adult humans, and even at one point a baby triceratops, which every viewer I've talked to, and then we're not talking about just professional paleontologists or biomechanists, every viewer I've talked to that has mentioned that scene has said how absurd that was. They're like, I don't know much about physics, but I knew that wasn't possible. And of course, because it isn't. I mean, it's totally absurd.
It's like an eagle trying to pick me up.
Yeah, it's like an eagle trying to pick a human. Yeah, it's ridiculous. And so you've got that, which just kind of comes across as silly. Alternatively, they could have used Quetzalcoatlus or Hatzegopteryx, one of these big-ass dark pterosaurs. Then what you would have had is a flock of animals with 33-foot wingspans that stand 14 to 15 feet tall, drop onto the ground like pseudo four-footed, because the hands end up acting as walking limbs because the wings fold up. These quadrupedal pseudo stork looking like things, like a stork from your nightmares, 15 feet tall. That's as tall as like the tallest giraffes. To put that in perspective, walking around, skewering people and eating small children whole.
Yeah,
that's what. Now, and that actually would have been more plausible in terms of the anatomy and the physics than what they picked.
So they would have they could have potentially kind of stabbed at them with their beaks and then done the pelican thing, just kind of kicked them back.
Just kicked them back and then taken them down through. Yeah, and you'd see struggling silhouettes of people going down the stretched out esophagus.
And then, of course, when they actually spread their wings to take off again, they're clearing tables of people. They're clearing cars.
Yeah, right, exactly. Just take people off the tables with their wings. It would be,
pretty badass.
It would be pretty badass.
And then they did the opposite thing with the mosasaur, the swimming reptile, right? They made him bigger and crazier than it actually was in life.
Yes, so they supersized that animal. So I actually have a little bit of research going on mosasaurs, kind of, because I do some swimming stuff as well. And it's all fluids. So it turns out the math is pretty similar.
Oh, that's true. Yeah. Fluid dynamics.
I'm cross-trained in fluid mech. That's how I got into that flight swimming kind of angle and things. Anyway, I do mostly flight, but I do some swimming and work on some mosasaur stuff. Mosasaurs, some of them did get quite large. The largest one would be about orca-sized-ish, which is, more than large enough to dispatch an adult human. But they, of course, had that finale thing where they went to dispatch a very large dinosaur, and so they supersized it. So it's about the size of sort of an average to largest baleen whale in the film, which is many times larger.
Were there any, I feel like I have one, I'm just referencing all of my little Carnegie Densor models around my office, like a Kronosaurus or something that looks like it was huge.
It was big. It was bigger than the largest Mosasaurus. It might have been a better pick, but it still wouldn't be that big. So they're, oddly enough, the only thing in the Mesozoic that we can say confidently was as heavy as living baleen whales were terrestrial. The biggest sauropods, particularly some of the big titanosaurs. So things like Argentinosaurus.
The ones that were more horizontal, not even the one that I think of as like a brachiosaur, which looks like a tank, right? And he's upright,
he's big and very tall.
But he's still not as big as those ultra ones.
Yeah, some of these titanosaurs were very beefy, very stocky, so we think we're probably heavier. Brachiosaurs and their close relatives were very tall. They were amongst the tallest dinosaurs. Although the tallest is thought to be Sauroposeidon, which was originally thought to be a brachiosaur, and now thought to be actually probably a group, part of another group of sauropods. So a little bit different part in the phylogeny. But there's a couple different lineages of super tall sauropods. But some of these titanosaurs were reasonably tall, but also really wide and thickly built, so they're extra heavy. And they would be, they'd be whale-sized. I mean, you're getting animals that are 50, 60 tons. That's up near, in fact, after a blue whale, the next largest animal in Earth's history that we're aware of, it was a big titanosaur.
Wow.
Then you get to the next,
next whale.
Or possibly. Yeah. Then you get to the next whale. I'll give that the caveat that I actually think those particular weight estimates for those particular dinosaurs might be a little bit overestimating.
Gotcha.
So I'm just using like what's out there in the literature. If you use what is, I think, more workers find agreeable, you've got two whales and then a titanosaur. Still,
that if anything, what that does for me is help me maintain perspective about how freaking big a whale is, because we've never seen like a titanosaur in a museum. It would be huge and it would be frustrating for them to like put that. Maybe there's one somewhere, like a full model.
There is in the American Museum.
Oh, there you go. Most of us though have seen like a slightly smaller version of a sauropod in a museum, and we can get a big feeling of that grand scale. But a blue whale, really, when we really think about how big that is, it's hard for us to comprehend how large a blue whale really is.
It's stupendously huge. It's the largest animal in Earth's history that we know of. Amusing enough, the American Museum of Natural History in New York has both a full titanosaur on display and a full-size blue whale model.
That's true, and that's above you, right? In that one really big hall where they do the sleepovers.
Yes, and it goes all the way across it. And so it's kind of funny. They do fun little like pseudo social media stuff where they post every so often where they pretend that the titanosaur and the blue whale are having conversations with each other about like the problems of being big, and it's pretty funny.
Aww.
It's really cute. But anyway, so you had these basically whale-sized animals walking around on land.
It's amazing.
There things like Kronosaurus and other Paleosaurs, these big short-necked, long-headed plesiosaurs, some of them were very large, but they still weren't as big as a large baleen whale. Bigger than the biggest Mosasaurs, but still not that large. And the trick might be where you feed on the food chain.
Okay.
So one thing that titanosaurs and baleen whales would have in common, even though they don't have many things in common other than being big, is that they both feed very low in terms of trophic level. So titanosaurs and other sauropods were feeding on plant material, so they're feeding directly on producers. Baleen whales are feeding mostly on things like krill and others, relatively small size invertebrates, just in mass numbers, which are basically then feeding on phytoplankton, so it's just one level up. So they're also low on the trophic scale. That probably is energetically essentially a requirement for supporting animals of that size.
It's just constant feeding of these high energy, like they directly made their sugar from the sun. And I'm just shoveling it in my mouth all day, every day, lazily.
Right, exactly. I'm just shoveling it. And remember, you're not going to have one of the things you don't have a problem with in that kind of feeding as well is success rate. Think about what a large baleen whale-sized predator would have to do in terms of of not only because it's not only feeding at higher trophic levels, so you have this, the energy pyramid basically it's working against is enormous. But think about how often it would have to be successful.
Yeah, like how many sharks or seals would it have to actually eat to make up for the requirements?
Yeah, it's actually it's really kind of astounding that we have sperm whales.
Yeah.
For example, which would be the largest sort of macro predator.
Or that when we think about some of the really, really, really large theropods, I mean, they did get pretty big.
Yes.
And, even T-Rex, like he's an enigma to a lot of people still, right? Because there's still sort of this ongoing fight about, is this pure fresh kill? Is it scavenging? Is it a mixture of both? How did they get enough food? Because they're massive.
Because they're big, yep. And the answer for most predators, incidentally, is, and this would actually be true for pterosaurs, since we're talking about the large pterosaurs, what they eat. Well, usually what you eat are things that are much smaller than you, even if you're a pretty powerful predator. You look at what wild cats and dogs and things eat. It's usually something that's significantly smaller than the total mass of predator chasing it. So that usually means it's smaller than the individual predator that is
there's some weird
predating it. But of course, if you have a pack, then you really the comparison is you total up the mass of the pack versus the mass of the animal. And what you'll find is that not always, but usually they outmass it.
That's why like P22 eats mule deer. It seems like a bigger organism than the cougar, the puma that's feeding on it. But mule deer travel in packs. Deer are like...
Oh, I meant the other way around, in the sense that
okay.
like the pack of predators will outmass the individual animal that they cull from the herd. The reason P22 is eating mule deer is twofold. First of all, cats break the trend a little bit.
They do.
They're particularly good at eating large
big
prey.
Things. Yeah, we think of lions.
There are large prey specials, and so we're a little bit skewed in our thinking because we try to like put these same kinds of ideas on the dinosaurs. Think, T-Rex is going to attack an adult Triceratops. No, that's suicide. Yeah,
because that's what we see on like the nature documentaries.
That's what the nature. They always do. No, it's going to eat a young Triceratops because it's not an idiot. Probably not super bright animal, but not suicidal.
Yeah.
But big cats are particularly good at eating big prey. The other thing is this. They'll say, it eats mule deer. Notice they don't tell you what age mule deer.
That's true.
Because they don't want to upset you with the knowledge that usually what it did was ate a cute little fawn mule deer.
Bambi.
Yeah, it's murdering Bambi. Yeah. That's what it does for a living.
And also koalas now we know.
Yeah, and also koalas. Yes.
I love that.
Oh Lord. Yeah. So the bottom line is that predators mostly predate juveniles, even big, powerful things like lions. If you look at what lions predate in the Serengeti, for example, and other locations, they are mostly catching juveniles. Interestingly enough, this is the interesting part, they predate the juveniles of large animals more often than the adults of small ones.
Huh. And that's probably having something to do with nutrition?
It probably has to do with the fact that juveniles are dumb. And I'm not kidding. It's because
that's true. They're easier to catch.
They're easier to catch. They're naive.
Yeah, and also because they'll also predate like injured animals, right? You know, just whoever's the gimpiest, kind of the dopiest looking in the herd.
Yeah, gimpy adults and juveniles who are usually stupid. The catching the adult of anything is really tough in the wild because that's an animal that has survived.
Yeah, it's selected.
Growth.
At that point, we know that it's been able to buck off other predators.
Predators, right?
Yeah.
It outruns them. It tricks them. That is a veteran. It's probably been beaten up a few times and survived. It's outrun things. It's like, dude, I've been around the block a few times. This is not my first rodeo. Don't even. It's not. So it's not just about size, although that's important because the adults of a lot of animals become too large to have successfully attacked. But it's also just the fact that they're just the adults are too savvy.
Yeah,
they know they're
smart.
They're smart. They've learned that you can't go over there even though there's some really juicy things to eat because that's a spot where you don't have good vision and the lions get you, which is what happened to 3 of my siblings that I watched get horribly killed and eaten. So I don't go over there.
And that's probably the main focus of mom training juvenile until it's finally weaned is like, this is how you eat, this is how you don't get eaten.
Yes.
This is like the 2 things in life you have to know.
Put food in your face and don't die.
Yeah, exactly.
Rinse, wash, and repeat. Just two different, yes, and eventually mate, but that comes later. So just for now, just put food in your face and don't die. And so being a juvenile is rough, you know, and it's and the ways that they get predated. I just saw a really cool night vision video where they had it set up. They were watching a nest day and night of hawks. And in the middle of the night, because they caught that video on all the time, they caught it. An eagle owl came in and pulled a mostly grown baby hawk out of the nest.
Wow.
Just came in at night and just ripped out. Of course, the hawks can't see worth a damn at night. And the owl, of course, sees just fine. And it just, and you see on the video the other siblings just like, what just happened? what the heck? Dude, you there?
Yeah, like,
where are you? Hey, why am I alone? And it was just,
no.
and it was just kind of like brutal and awesome at the same time. And one of my buddies posted on social media, posted on Twitter, and he just he added the caption. He just said, how are there still babies of anything?
Yeah, seriously.
How are there still? How do they
strength
survive?
in numbers, I guess. That's really what it is.
You have enough of them that eventually.
It's why, like, how are there still baby penguins? That's a question.
That's a question. Yeah, everything's that can murder a baby penguin. Yeah. And then anyway, so the same would actually be true for some of these large pterosaurs. I could ask you, what the largest pterosaurs probably ate, and they are built based on their cranial anatomy and other aspects of their terrestrial gait and things. They're built to eat small things on the ground. They could fly, but probably most of these an escape from big predators or to cover ground or whatever you need to do. They're the big ones, the real giant pterosaurs are probably eating small prey on the ground. And you look at the Mesozoic and you go, oh, well, of course there's going to be more animals in that with that ecology because there's more small things on the ground. Yeah. Because the Mesozoic was a weird time period compared to ours, or ours is a weird one compared to theirs, how you look at it. But that was a world filled of giant adults that were all we'd like to call R-selected. That is, they produce a large number of babies, most of which don't survive.
Yeah.
So it was really a world filled of meatballs. Like the world wasn't unlike the murals you see in every museum or every documentary ever, where we show like a world filled of adult giant dinosaurs because it looks cool and you want to fit them all in. In reality, what would be a landscape with the occasional big giant thing that's a veteran that survived for 40 years and is now so large it's invincible.
And it's probably all scarred
up. It's
up.
Scarred up. This big scarred titanosaur that's 40, 50 years old and just untouchable because it's 50 tons and it's just wandering along, just putting things in its face, and it just generates a tremendous number of eggs twice a year or something.
And crap.
Just
eggs and crap.
Just eggs and crap. Just stuff coming out of the back of it all the time. And it's just marshmallow, and nothing touches it because, I mean, one tail whip from this thing will decapitate anything in this environment. But and it's oblivious or nearly oblivious to what's going on around its ankles, which is essentially a sea of destruction. As all the baby titanosaurs and baby everything else try in vain to scramble under cover from the onslaught of theropod predators and pterosaurs from the sky and terrestrial crocs that were in the Mesozoic and early some of the earlier snakes. For example, there were some pretty big snakes. We actually have one fossil of a snake associated with a nest, dinosaur nest. So it got killed by the same sandstorm that killed the nest. It was probably trying to eat one of the babies or an egg. Like, you're on this onslaught of baby killers from every angle. And the only reason if you survive is probably because you got into cover a little faster than your sibling, and you've got 50 siblings, so it's just stats,
Wow, what a crap time to be alive.
Well, it's a fun time to be alive if you're like one of the pterosaurs or an adult or a theropod, but
it's a fun time to be alive if you're huge.
If you're huge, if you've gotten through all that, but it's a very tough time to grow up in.
Yeah, especially if you're Quetzalcoatlus, who is amazing. He's an amazing pterosaur. It's funny when you see the way you were talking about they feed on the ground and the way that they walk, where their wings kind of fold up and point to the sky, and they're like these little quadrupeds. And they're just huge. Like when we think about, you said 33-foot wingspan, but like, well, how big is that really? That's like an airplane, right?
That'd be a small airplane. Now, of course, it's not going to weigh anything near a small airplane because it's attached to a relatively small body. Actually, these things are weirdly proportioned. The head on big cats. Now, the caveat here is we actually don't have a complete skeleton of the large Quetzalcoatlus. We do have 6 skeletons for a smaller. A set of smaller cats, and so we use those to try to fill in the gaps. From the big cats, what we know is the wing. We have a close relative at its size, from which we know part of the skull, part of the neck, and other parts of the wing, and then or overlaps of the wing really, and then we have the full skeletons of the little guys. So there's a certain amount of extrapolation here.
Yeah.
Nonetheless, assuming that the proportions of the little guys are correct, the head on that animal would be about 3 meters long.
Oh my God.
But the shoulder to hip distance would only be about 3/4 of a meter long.
Oh, crazy. So massive head, massive wings, tiny little body.
Yeah.
Long tail?
No,
No,
long tail on
short
that
tail.
one. Some long tails on some of the early pterosaurs. Most of the later ones have short tails.
Gotcha.
So what you have, if actually, and the legs are long but relatively thin and not terribly powerful. In most, especially the later pterosaurs. So it kind of matches the body. So
Yeah.
a pterosaur, especially a Cretaceous pterosaur, basically looks like you have a normal proportioned reptile in the back half, and you've bolted it to this giant-headed, giant-armed monstrosity in the front, and you've just soldered the. It's like you got behind your project deadline and you didn't get a chance to finish the back end. You're like, well, we have some of these regular reptile back ends back here. Well, those don't match at all. Well, look, we got 2 hours to finish this. We just got just weld those together and ship it. Got to ship it. And that's basically what these things look like. Which is one of the things. My first big pterosaur project when I was a graduate student, the thing that kind of first cut my teeth on the pterosaurs and I got known for and working in the field was on working on pterosaur takeoff mechanics, which I still do some of. And
how did they get lift? Because
right,
they've got to have power in their legs to be able to jump, right?
Well, you need power in the limbs you jump with. But if you walk on your hands and feet, you've got 4 jumping limbs, not just 2.
Gotcha.
And that ended up being the answer I came to, is that actually the trick is that, well, they're quadrupeds, so they jump quadrupedally too, presumably. So they don't. So yeah, the legs are adding a good, and the legs aren't useless or anything, but they're just, like I said, kind of average reptile legs. So they got average legs, and then way more than average arms and pecs and everything go with that. So basically, it's the muscles of the back, chest, and proximal wing that are doing most of the work in terms of getting them up, particularly the vertical part, I think. So getting the exact kinematics, this kind of thing, of course, is largely sort of speculative work. I can do the physics based on the anatomy and launch and aerodynamics in terms of what kind of speed they need coming out, and I can do all that.
And how high do they have to go to be able to unfold those crazy wings?
Exactly. And I can work all that in, and I can give you a series of plausible launch hypotheses. And the one thing they all have in common is they all involve a quad launch. That is, they have to be pushing with the hands and the feet, otherwise it just doesn't work for anything above about 4 or 5 meter wingspan, which is huge by our standards of living flyers, but that's actually a pretty average pterosaur.
Interesting.
So I figure most of them had to probably do this, and probably they all did. It's probably something that they inherited early on. Their ancestors might have been bipedal, but somewhere early on, pterosaurs went through a quadrupedal gait, and once they did, they suddenly had a lot more power in contact with the ground, and that gives you a huge boost in terms of being able to evolve large size, because now you can use a lot more of your available muscle power for your takeoff launch or your takeoff leap.
And that's somewhat newer information, right? Because one thing that I love about this exhibit is that it breaks it up into like flight, on land, over the water. Like it breaks it up to where they are and kind of what they do in those locations. But it also breaks up these different sort of aspects of their anatomy, and it shows historical drawings from paleontologists. Like, this is what they used to think based on the bones. And then they kind of realized doing a little work that they didn't just walk on 2 legs. They had to use the 4. And it's cool because this is the kind of work that allowed and continues to allow scientists to know how to show the public what these organisms actually look like, because you don't really know what they look like without knowing their biomechanics.
Yeah, that's a really good point. We're starting, I think, to get a much more realistic idea of how these animals would be built. There was some weird mental gymnastics in the past to try to make them ultra light, because it was thought that was really needed in terms of for the flight biomech. And actually, it's been relatively recent that you've had quantitative aerodynamicists working on pterosaurs. There are really 2 of them right now who are doing the bulk of that work. One of them is myself, and the other one's Colin Palmer out of Bristol in the UK.
And do you guys collaborate ever?
We do.
Yeah,
we do.
I like that about science,
which is fun. Yeah. No, actually, we're good buddies. We get on very well.
Cool.
Colin and I have different backgrounds. So I'm a biologist first who cross trained into engineering. Colin is an engineer first who cross trained into biology and paleontology.
Very cool.
And anyway, and so Dr. Palmer has done a lot of wind tunnel stuff, and knows an awful lot about aeroelasticity and things like that. So how you keep a membrane wing from fluttering, stuff like that. Because he used to work on sails, on racing, high performance racing sails and things like that. And he's a bit of a legend actually on that. And then And then I know a lot about dynamics and muscle and bone limitations, things like that, because I'm coming at from that angle. And so we do our own independent stuff. We also join forces from time to time, and like we join forces to try to look at what the largest a pterosaur could be and still launch. So trying to look at the maximum possible size for a pterosaur.
Where does it become landlocked?
Yeah, exactly. So we worked on that together, which is pretty cool. Have that written up soon. We've already presented in a couple meetings. That's pretty fun. And actually that's starting to make things a little bit more sophisticated, because when you start taking the kind of approach that he and I take, you start including things like, well, the wing has to be a certain thickness in order to keep it from fluttering. It has to have certain materials to keep it from fluttering. Certain wing shapes are possible and other ones aren't, because it has to be tensioned.
I like
the center
that in
of
the
mass
exhibit.
has got to be in certain places, so that means the center of lift has to be in other places. It tells you where the wing position has to be. Things like that.
So complicated. In the exhibit, it had this really great section on the wings and like what were they made of and how were they shaped, and these different fibers that reinforce the wing, and then compare it to a bird, compare it to a bat. I thought it was really fascinating. You could kind of go up and you could like touch it and see how it would fold in order to be able to, because this is a massive wingspan that has to be able to like fold up completely.
Yes. Yep. So there were probably specific fold lines that it tended to repeatedly
like
fold
a fan.
on. More like a fan, like a little fan. A little bit more than sort of a stretchy rubber thing. The classic animations tend to kind of make it super rubbery, really stretchy, and then it just kind of, so it sort of collapses in all directions equally and then kind of stretches back out. But actually, if it was that elastic, it would flutter in flight.
So it's almost halfway in between, because like whereas a bird has that really beautiful kind of fanning out of the feathers that sort of stack, it's somewhere in between.
Somewhere in between.
It's neat. I love it.
A wing has to be actually reasonably stiff, the material, unless you can stretch it across a number of preferably 4 or 5 or more sort of battens across it. So pterosaurs didn't do that. They were suspended from a giant fourth finger, so they had to have material properties in the wing, which we actually have some information on from some fossils, because you get soft tissue preservation in some of these fossils. So we have the internal structure of the wing for some of them.
So cool.
And so they be a combination of proper tensioning and muscular action, as well as, say, keratinization and things of the wing, that's going to provide the stiffness they need. Birds get it from the fact that feathers are naturally fairly stiff.
Yeah.
Now, bats have a wing that isn't all that stiff, but they're getting by doing the other option, which is they have 4 other 5 fingers stretching it, so they can get away with this hyperelastic wing. And there's advantages to both of those strategies, but it's trade-offs like everything else. But we're now starting to look at the kind of thing which was really pretty recent, those sort of material property kinds of estimates, which is kind of cool. And it is mentioned in the exhibit. There's a lot of good visuals for that. There's some cool interactives. In fact, we even worked in some of the basic physics. It's rough, but we did work in some of the basic physics into a flight simulator.
Yes.
Where I imagine you got a chance to play that. So you get up on the platform.
I didn't get to because there were kids that were waiting, and I didn't want to get in front of the kids. But we actually, the Nerd Brigade and I, this group of friends that everybody listening knows about the Nerd Brigade by now, we're actually going to go back and record some videos for the museum in the flight simulator.
Nice.
So we're really excited to go try it. I will probably crash. I crashed a 747 flight simulator, so
gotcha.
I have a feeling I will crash a pterosaur as well. But
yeah, not quite as stable as a 747, so that might be a challenge. But it's cool, and you can, and there's diving mechanics that we added, and water launch mechanics that we added.
Some of those kids were good. I was watching; they
kids
picked it up really
good.
fast.
Yeah, they get pretty good. Yeah,
surprise! It's fun. You get to stand there and flap your wings and be a pterosaur. And just last question before I get into the last questions today is that, just to be clear, pterosaurs, as far as we know, the first organisms ever with powered flight.
First vertebrates.
Because of course there were insects prior to that.
Yeah, insects beat them to the punch by over 100 million years, which is actually kind of another interesting thing. There's one group of pterosaurs in particular called neuronathids, one of which Gelhopteris is really featured heavily in the exhibit, and that we think, based on multiple lines of evidence, and we can sort of robustly conclude, we're able to hawk and probably specialized in hawking flying insects on the wing. Up until that group of pterosaurs evolved, probably no vertebrate animal could reliably catch flying insects on the wing. Maybe when they landed, but not on the wing, which means there was over 100 million years of time where if you were the largest insect and you took the largest flying insect and you took flight, you were invincible.
That's
for 100
amazing.
million years. And then they just ruin the party. Pterosaurs get in the, like, oh man, vertebrates are flying now? They'll let anyone do this. I mean, and there were unpowered vertebrate flyers before that. And they could probably occasionally catch an insect in flight.
Meaning gliders and things
Gliders
like that.
of various types. And they could probably, and just like living today, they probably occasionally caught an insect on their glides. But usually those animals catch insects on leaves and twigs and things, and they're using the gliding to move between feeding patches effectively, and also escape
So
danger.
if you're flying over high enough over open water or something, there's nothing's going to get you.
Right.
Yeah. Up until
pterosaurs show up. Yeah. And particularly when probably in the Jurassic, really, when you get these ornithids, even the Triassic pterosaurs, they have insect feeding tooth specializations, but we don't think they were eating small insects on the wing. We suspect they were eating large, crunchy things on the ground.
It is interesting to see how incredibly diverse, this group of organisms, we only know about 150 species, and it had such a very specific ecological niche, but like how diverse, from beaks to tooths to almost these like baleen-looking structures, from eating everything from plants to insects to other carnivores even. It's fascinating to see how much diversity within, I guess it is a relatively large amount of time, and obviously there were more species than we know about because obviously they didn't preserve very well. It's just fascinating to see how crazy different these guys were.
They were really weird animals with their giant heads and
just those
and
frills.
membrane wings and
so
just
different on the frills.
Yeah, the frills and head crests, they're really cool anatomy creatures, and the role they would have played ecologically is very interesting. Even though we don't have that many of them, we know there was a wide diversity of them. We know they are living in all these habitats, and the role of flying animals and large flying animals, in particular in the modern ecology, is very interesting because one of the things they do is they move material over long distances in ways you wouldn't otherwise.
They're migratory.
They can be migratory or long distance foragers. They eat an animal in location X, and then they pass waste in location Y or breed in location Y. They're moving energy and nitrogen and carbon around in really unusual ways for an animal. Which means that even though we don't have that many species, we know based on the diversity that we do have that there was probably a lot more species we'll never find living pretty much everywhere. We do have fossils from every continent and playing this kind of ecological role throughout the globe in the Mesozoic. So pterosaurs were probably very high ecology impact players, basically. Regardless of what their population sizes were like, we won't ever really be able to know whether they were terribly numerous or not.
But there must have been
others weren't.
A boom from before there were pterosaurs to after pterosaurs. There must have been an uptick in diversity in different regions of the globe.
Sure. Yeah, I'm sure there were. I'm sure there was. They probably went from a relatively low level of diversity in the Triassic to extremely diverse in the Jurassic and Cretaceous, and then all of a sudden you have these powered flying vertebrates on the map, and it's going to do, like I said, a lot of weird things to the global ecology because of their mobility, and that's really interesting. And big flying animals, in particular, are especially mobile, so it really affects the global ecology in kind of cool, unique ways, which is interesting because they become kind of a model for us understanding not only some interesting mechanics, but also thinking about macroecological problems and the role of flight and in the role of aeroecology in the living world.
Mike, I could keep you here for hours. It's so terrible. I want to give you your weekend back, but before I do, I want to close this extra long episode. Thank you so much for
it's no problem. My wife's on a 24-hour call, so I'm on no
I'm
no
cool,
hurry.
We're hanging.
I'm cool. Yeah, whatever. I got I'm no normally what draws me back home is spending time with her, but she won't be back until tomorrow morning. So
now it's just Takeout City, I guess.
Yeah, exactly. Takeout City and talk about pterosaurs.
Yeah, exactly. I'm so excited. First of all, I have to say, because we've been trying to get this on the books for a long time. I'm glad our schedules were able to align and we were able to do it.
Absolutely.
Before I let you go, I close every episode with the same two questions, and it's really cool to see the diversity of answers based on who people are, what they do for a living, all that good stuff. So I have to ask you the same two as well. These are big picture questions, but you can answer them however they matter to you, whether it's personal, global, whatever. So the first one being the more depressing question is that when you think about the future, what is the thing, whatever that thing might be, that keeps you up most at night, makes you the most concerned, the most worried? But then on the flip side of that, what are you most hopeful for and optimistic about?
Those are great questions.
They're
So
tough.
yeah, they're tough. I'll just go with the first thing that comes to mind because I
Mm-hmm.
think that's probably the most honest answer I've got. The first thing that came to mind with the first one is it's a broad answer. I'll admit is biodiversity conservation. And in fact, my master's is in conservation biology. That's so I kind of went from that realm then into paleontology. And some people have asked me like, well, why'd you go, if you're so passionate about conservation, why'd you go into paleontology? So, well, part of the reason I'm interested in paleontology is, as I mentioned, sort of the biomechanics and performance of extinct animals, and they're just cool, awesome animals. But I'm also interested in setting the context for understanding our modern biodiversity and its uniqueness and the amount of evolutionary history that you are preserving or potentially losing if you don't preserve certain groups of organisms. So there is that context there, and there are days I have to say that I do think about maybe transitioning back more into a more policy driven conservation biology kind of role at times. I don't think I'll go back to it full time, but like leave paleontology or anything. But I might snake my way back in there at least as a sort of a side.
Does it worry you that you would feel? I shouldn't say helpless because obviously we're not helpless and there's so much that can be done. But does it worry you that you would feel sometimes really frustrated or cynical because kind of when it comes to conservation biology, we're up against so many hurdles?
Yeah, it was frustrating many times, and it still is, and still would be. There would be a lot of frustration there. That's one reason that it keeps you up at night and is concerning. But in terms of the hope, there's multiple things I'm hopeful for. One of them is that as much as frustrating, as much as I'm concerned about conservation in the future, one thing gives me a lot of hope is I think increasingly it's being thought about more broadly, more by a larger percentage of the population, and I also think it's being thought about in ways that are more realistic. And because it used to be that you kind of had just two sides, two very emotional sides sort of shouting at each other. One side was like, look, we have to preserve everything, and if you don't agree, you're a horrible person. And another side being like, well, I kind of want to eat first, and I live in a place that has very low GDP, and we have to use whatever resources we have. Sorry, you guys are horrible and out of touch.
Yeah.
And they both had their merits, and they both had their blinders on to a certain extent. And I think we're getting more communication and more realistic outlook on what biodiversity is and what it means and how do you preserve it. And there's been some success stories as well. So that gives me a lot of hope for the future. And I also have my more general kind of hopeful for the future comment. I'm a real technology optimist. I partly because I was inspired in my youth by reading a lot of Asimov, who was a real technology optimist, and I liked his comment. He says, if ignorance or if knowledge can create problems, it's not by ignorance that we will solve them.
Yeah.
And so I'm hopeful about not just conservation, but a wide range of problems in that we are becoming more knowledgeable as a species. We are trading that information more readily than we used to. There's still plenty of glitches and bumps in the road, and I'm not saying that the information age is without its flaws, but we are learning more. We know more than we used to. Our technology is improving, and even though technology can create some problems, it creates more solutions and it creates problems. I really do think that's the case.
We're capable of doing more with less now. We're capable of being more efficient in our problem-solving strategies, and that's only going to continue.
Absolutely. We get higher efficiency. Increasingly, more and more populations of humans have the opportunity to care about things like conservation because technology has now become, maybe in their location, for example, more affordable to the point where they can now use high efficiency solutions where they had to use a low efficiency solution before because it was the only thing they could do. It was either that or die. And now it's, I'll use the high efficiency solution. And now maybe they have more time or more money, more whatever it is on their hands, which they can now think about using for working towards some of these global problems. We have increasingly a population that can work on global problems. The trick, of course, is that global population is also increasing quite rapidly, which has its own problems, as per the conservation note. But I guess my optimism is that the efficiency and technology will improve faster than the growth rate.
And it may actually even affect the growth rate.
Well, ultimately,
overall.
I think it will. Yeah,
with
ultimately,
the
it will.
education that comes from that.
Exactly.
For sure.
Exactly.
Well, gosh, this was a fascinating chat. I
Thanks.
want to do more of that. I'm gonna like bug you in about a year to come back and we'll
Yeah,
learn all
whenever you
about it.
want.
We didn't even talk about your field work much.
Yeah.
We didn't. It's so
I just got
terrible.
I
There's
just
so
got
many
back from New
things.
Mexico in the field. We can talk sooner than later if you want.
Awesome.
I'll pop back by. And
I would love that.
We'll talk about what it's like to find dinosaurs in the desert.
Yes. Oh my gosh, I would love that. And about exactly what you're focusing on now, all that good stuff. Are you a social guy? Like, are you on social media? How can people who are listening to the podcast say hello?
So I am a social guy. Friday nights, no, I'm just kidding. But no, in terms of
You
the
are.
kind of
Don't
social,
I follow you on Twitter?
yes,
I
in
think
terms
so.
of the kind of
Okay.
social you're talking about, yeah. So I have a Twitter account. I have an Instagram account, which is a little more recent. I've been playing with a little bit.
Oh, cool.
I have a Google Plus account. I do not have a Facebook account. That's the one big one I don't have.
Yeah.
And there's all kinds of reasons why I don't, and don't have to worry about that. But yeah, on Twitter, I have a handle. It's AeroEvo, AeroEvo for aerial evolution, because I study the evolution of flight. And I'm searchable under my real name on Google. So I'm on there. I have a few other USC pages and things like that we're working on. But yeah, so those are good places to kind of find me on social media and ping me random questions and nerd out a little bit and all that kind of good stuff. So that can be a fun community to chat about these things in.
Yay for nerding out, and I know that the listeners are going to do that. They will probably take you up on that. Michael, it was so much fun having you on the show. Thank you so much one more time for sitting down with me.
No problem, Cara. It was a great time. I love this.
So great. And everybody listening, thank you so much for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.